All right, welcome everyone. My name is Craig Sipes and I am the STEAM coordinator for Local District East. Very happy to be here with you today. In the chat, you will see the sign in. Please go ahead and sign in. Put also your last name, comma first name, your grade level, and then whether you are an Amplify or a FOSS school. Oh, there's Lillian. Hi, Lillian. And presenting with us today, I'll let folks introduce themselves. In-Young, you're here too. Let's start with Lillian.
Hi everyone, I'm Lillian and I'm the science coach for the Huntington Park, Walnut Park, and Vernon community of schools. Welcome.
I'll go next. I'm Erica Lee. I am science coach for elementary in the northern communities of East LA, Lincoln Heights, El Sereno, and Boyle Heights.
Hi, my name is In-Young Lee and I support science in Southgate and BCM. I'm here to support in the chat today.
Thank you. And we're very happy to see you all here today. All right, so today, our professional development is the third in a 4-part series. The series is called Ambitious Science Teaching Practices, where we are diving in to look at the practices, the teacher moves that support the student moves, which are the science and the engineering practices. Today, the title is Supporting Ongoing Changes in Student Thinking. This is number 3 in the 4-part series. So to start off with, which television teacher are you feeling like today? So we're going to do this as a waterfall. So look through, you've got 9 options. You might be familiar with all of them or some of them. And go ahead, you can just go off of what they look like in the pictures if you're not familiar with them. Type into chat, but don't hit enter yet. We're going to do a waterfall. Sorry, Melissa. Don't hit enter yet. We're going to do a waterfall. You can do it again. Okay. Is everyone ready? All right. Let's do 3, 2, 1. Waterfall. All right. We've got lots of magic school buses. We've also got Bueller. We've got what is 4 again? Is that SpongeBob? What is all right. Good. All right. We're glad you're all here today. Good to see you. All right. So today, as we're going through today's slides, we'll ask that you're fully engaged. And what that means is we'll ask that you stay muted unless we're having a question, and you can unmute and speak. And we want to hear what you're thinking. Please keep your cameras on, respond to chat or to questions when prompted, and we will from time to time have a cold call. So objectives and outcomes for today: that engaged participants will be able to ensure students understand why the activity makes sense and why it makes sense in the place in which it is within the unit, to help students bridge the activity with a larger science idea, and to support the development of students' academic language using the activity as a context. So this is in line with our instructional foci for Local District East. We want to continue making sure that we have deep clarity in learning goals. This 4-part series is particularly connecting to precision of pedagogy. How are we building those teacher moves? And then also we want to attend to student voice. So as we're going through, think of ways that student voice is empowered. So first, what is NGSS standards-based instruction? So first of all, science is about knowing. Those are the DCIs. And as it relates to school and to NGSS, it's what are students trying to figure out? But NGSS is three-dimensional, and it's not just about knowing, it's about how do we know? How do students figure things out? And this is the science and the engineering practices. These are the doing part. When we talk about standards-based instruction, it's not just the knowing, it's how do students figure out what they know? And they do this through the engagement of science and engineering practices, and also thinking like a scientist and an engineer. These are the cross-cutting concepts. So how are students thinking about it? And then this comes to one of the big anchoring things in science education, which is the anchoring phenomenon. What is this storyline that we're building with students? Why are they engaging in what they're engaging in? Why does it matter to them? And what is that second layer of figuring out? And that's the phenomena, the storyline. So we think of the phenomena as the anchor, and that as the phenomena forms the anchor, it also sets in what we call the backbone of the unit, which is the unit arc or the storyline, where students start off with an engaging phenomenon. They ask initial questions, they put together an initial explanation, they go through learning activities, which help to construct knowledge. These are practice-centered learning activities. They go back and they revise their explanation about the anchoring phenomenon. They build on their knowledge some more with practice-centered activities and finalize their explanation. So this whole thing together, it helps to create DOK 3 and 4 opportunities for students to really figure out how their world works. Our local District East science foci for this year are the science and engineering practices 2, 6, and 7, developing and using models, constructing explanations and designing solutions, and engaging in argumentation from evidence. What's common amongst all three of these is that they all call upon students to make a claim, to provide evidence, and to justify that evidence as meaning something, as connecting to the claim through scientific reasoning or some other form of justifying. How do we help students to do these things? We help students to do these things through the teacher moves. The teacher moves are what we call the ambitious science teaching practices. And you see the 4 of them there. We've gone through planning for engagement with important science ideas. This is about setting up the phenomena, understanding the phenomena and the arc of the unit. That was our first PD that we did together. Last PD that we did together, we were looking at how do we elicit students' ideas. And today we're going to be going into number 3, supporting ongoing changes in students' thinking. And so this is a nice little handy overview, once again, of the 4 ambitious science teaching practices. These are the call outs of those 4, and then the look fors of them. So when students are, when teachers plan for engagement with important science ideas, what are you going to see? You're going to see a connection to the real world. You're going to see this, they're learning to be contextualized through a phenomenon. When the teacher is figuring out how to elicit student ideas, what are you going to see in the classroom? You're going to see students asking questions, or you're going to see students explaining how and why they think the phenomenon happens. And then today, in supporting ongoing changes in thinking, when this is engaged, then this is using all activities and lessons to explain the phenomena. How does this all come together? Through multiple extended opportunities to learn, giving the students the opportunity to revise their thinking based on what they're learning. And that'll lead to the next time when we talk about pressing for evidence-based explanations. These are the teacher moves.
So now we're going to engage in activity. In the chat, you'll be receiving a link to a participant slide deck. You'll want to keep that open throughout this PD. And you're going to be going into breakout rooms based on your publisher to review a learning activity that students could engage in. So if you're FOSS, you'll be looking at the FOSS activity. And if you're Amplify, you'll look at the Amplify activity. Once you've reviewed the activity, have a discussion around why the activity is a sense-making activity, and then discuss which science and engineering practices that your students would be engaged in while participating in this activity. You'll also get a link to the NGSS progression, so you can look for which SEPs, which science and engineering practice the students might have been engaged in, and just have a discussion around that. If you have time, you've already finished up looking at your publisher's activity, you can always look at the other publisher's activity. And when we come back, we will share out our thoughts and we'll look back at those questions. So we are going to open up the rooms. If you are not in a room, I see. I will open up a new room. So go ahead and join your room. Miss Kim, are you having trouble joining your room? Oh, there she is. No, just kidding. You didn't make enough rooms. I should have made more rooms.
There's only one FOSS.
Even go over the other publisher's activity. Let's take a look at just our questions again. So we're looking at how these activities support the anchoring phenomenon, and also what science and engineering practices students are engaged in. So let's go ahead and look at our first activity. First one is a investigation and activity from FOSS. So we selected one from a series from this unit, and it doesn't just, I know we only have one FOSS teacher here at the moment, but if you had a chance to look at this activity or have experience with this, because we used to have FOSS, perhaps you can share out what makes this a sense-making activity. We can look at both this slide and the next one as well. What makes this a sense-making activity, and what science and engineering practices would the students be engaged in? You can unmute, share in the chat. Miss Garcia, is it all right if I ask you to share?
Yeah, I was saving, but it's fine. So basically what we discussed is that the students are making a prediction of what they think is gonna happen. It's like they're gonna throw two balls with different weight, and they're gonna make a prediction of what they think is gonna happen, what ball. So it's based on weight. So they're gonna make a prediction, then they're gonna put the rams and experiment what's gonna happen. They're gonna record data, and then at the end, they're gonna analyze and then kind of keep building their knowledge based on their experiments and the data they gathered.
Yeah. If we come back to one slide before, sorry, and we look at that anchoring phenomenon, right? Two children are bowling. One uses a 12-pound ball, the other uses a 8-pound ball. And then come back to the actual activity within FOSS. They're going to record that data. They're going to carry out an investigation, right? They're going to plan and carry out. So we've got our science and engineering practice there. And then they're going to record that information and yes, eventually come in and analyze that. What does that mean for us to help answer this anchor phenomenon? So thank you for sharing, Ms. Garcia. Moving on to our Amplify activities. We have a lot of Amplify teachers here. So if anyone could unmute and share out, type in the chat.
I can share. So this activity is centered around food. So we have two salad dressings. One is mixing into different layers, and then the other one is mixed completely. So students are having a discussion about why is this salad dressing breaking up into layers, and this other salad dressing not breaking up into layers. One of the things that we discuss is what makes this kind of activity more engaging is that it talks about food, and we all eat food. And I think when kids realize that, you know, there's science in the things that we eat, it gets them excited.
Absolutely. I love your comment. Yes, we eat food, right? Food science. So we all eat food. It's connecting to what is real in real life to them. I'm sure they've seen salad dressing do this sort of separation or non-separation in this case. So it's connecting to a real world phenomenon, something that they may have experienced. If you take a look at the next slide with the activities that they're going to be doing, right? Again, we're looking at, can anyone have maybe a guess, educated guess on what science and engineering practice is involved here?
Fluid dynamics, chemical, stuff like that.
Okay, so yeah, it is definitely a chemical. We're talking about matter and learning and understanding the chemical properties of things. Where students are still going to be engaging in that planning and carrying out investigations. So looking at science and engineering practice 3 there, how they're going to record, and eventually this information is data that they're collecting. They'll model. It's connecting to modeling later on. And also right here, you can see that they have a digital tool that they're going to be using, a simulation where they look at that micro level of things. So thank you for sharing. So we showed these activities because we wanted to make the point and really help us to understand that these are activities that really count as sense making. So here's a list of, and it's not fully complete, but here's a list of activities that we would consider to be sense making for our students as they're engaging in the science, right? Understanding these big ideas. If you can think about your classroom, you know, are these some activities that you've used before? And just a rhetorical question for you to think to yourselves, right? I'm sure we've done many of these before. So these are activities because they really do help our students to understand and to make sense. It's not necessarily a one and done, and then there's no connection to what they're learning. However, if we look at the next slide, we have a short list of things that may not necessarily count as sense making. It doesn't mean that these activities can't happen in the classroom. These activities can be adapted to become sense-making activities for our students to explain these big science ideas. So you'll see Bill Nye there, and you know, I'll admit it, I'll be the first to admit, have I used it? Yes, I have. Have I used those videos? Absolutely. But could I have, Craig shaking his head, but could I have done something to make them and improve them to be more sense-making? Absolutely. Connecting it to the big science idea. Now you've seen this, perhaps a demo. What does that have to do with what we're learning right now? So connecting it to these big science ideas. Here is some images of something you may have seen or done yourself as a student. Let's take a look and see, what is it about this that would not make this such a great sense-making activity? We're just going to share out here. Chat, open forum, unmute. So we have the model of the solar system.
It's kind of like memorization, but in a sense of just in a model. There's no other, there's no further research, hands-on activities with it. To me, it's more memorization.
Mm-hmm. Yeah, I mean, We have to know the order of the planets, right? This is what it's asking students to do, know the order of the planets, maybe the size in relation to the sun. But what are the students doing to really make sense of what they're learning here? A quick note, in FOSS and Amplify, there are examples of where students making models. However, there's a slight difference in that sense making because they're really looking at scale. They're looking and understanding, okay, how do these planets, how are they distanced apart in relation to the sun? So they're thinking about scale, they're thinking about location, and it's not just here's a styrofoam ball and let's color it nicely and put them in order. So we're really thinking about, okay, how can we make these sense-making activities? Thank you for sharing. Our next slide here is, we're making this connection to why we are teaching these lessons and doing these sense-making activities. So if you notice, this is a common image that we've shown in our PDs of this anchoring phenomenon, the purple cloud connecting to each of these lessons and investigations, and how each of them really do support students' thinking, students' changes in thinking over time. So in order for us to do this, we have to engage them in meaningful activities that help them understand the parts of that anchoring phenomenon, engage with big science ideas, and do so multiple times throughout a unit. As I mentioned before, it's not a one and done, but a series of lessons that help build understanding of a specific real world phenomenon.
And if I could jump in, Erica, to say this a little bit differently. So each learning activity, the students are engaged in figuring something out. That's one layer of figuring it out. And the other layer is that each of those pieces serves in a larger sense-making activity, which is what Erica has been talking about. The larger sense-making activity is really figuring out that anchoring phenomenon. So students are really engaged in two levels of making sense of things. One in the moment, and then the other one stepping back to see how does now what we just did, how does this connect to help us make sense of something else, of this other real world thing. Thank you, Eric.
I'm going to pass it on to Lillian now.
All right. Thank you, Erica, for guiding. Are you able to hear me okay? Yeah, okay. So thank you for guiding us through some sense-making activities. And so as mentioned, throughout the course of the unit, teachers plan for lessons and sense-making activities that will support students in building a better understanding of the anchoring phenomena. So let's take a closer look at the 3 sub-practices that are introduced in Ambitious Science Teaching Practice 3. They're introducing new science ideas, activity and sense-making, and collective thinking, revising models and explanations. So to frame the unit and you have a better understanding of Ambitious Science Teaching Practice 3, we're going to launch an anchoring phenomena for a sound energy unit. So we're going to go ahead and play the video clip. And as you view the clip, what do you notice and wonder? And feel free to type a response in the chat. And also think about if you can think of any scientific reasoning that will support an explanation for why this is happening. So Craig, will you go ahead and play the clip, please?
Yes, I'm sorry. I think I have to reshare. 1 second, please.
Okay, sure.
Okay, let's see if it plays the sound. Oops, wrong button. Okay. It's not playing this sound. Sorry.
Would you like me to try screen sharing?
Sure. Thank you.
Okay, let's see if this works.
Right, we're good. All right, so go ahead and type in the chat, or if you want, yeah, go ahead and type in what did you notice? And then also, what did you wonder? And maybe we could play it one more time, in Young, please.
Absolutely.
Thank you. I never get tired of seeing that video. We're gonna have to do a challenge, a science challenge.
Yes.
So Gabriel, thank you for sharing in the chat. I noticed that you said, I noticed that he shattered the glass after tapping it. Eric said, I noticed the man broke the glass, screaming at it. Carla says that she noticed, oh, it just went up. I lost you. I noticed the straw moving. I wonder why the glass broke. Sarah said, I noticed there was a straw in the glass. Lilia says, the high-pitched noise broke the glass. Okay, thank you all for sharing. And so with this initial anchoring phenomena, we're going to move on to our next slide. And so once this unit is launched with an anchoring phenomena, the students would normally create an initial model, and they will have engaged in several learning activities that support their own sense making. And looking at the unit activity planner, as shown here on the screen, we see how different activities help students make sense of the phenomena. So today we're going to take a closer look at activity number 2, decibels at a distance, and that's going to be our example. So in this activity, students carry out an investigation in which they use a sound source and record decibel readings at various distances from that source. They will also graph data points to show the relationship between the intensity of the sound in decibels and the distance in meters. So students can either use some kind of digital sound meter or an app like Arduino, which includes a sensor and it measures sound intensity and records a graph over time. So after gathering their data, students might notice that the sound intensity is less further away from the air horn. Students graph their data and the decibels at a distance graph. Students are then asked, how does this graph help us understand the singer? How the singer could shatter the glass if you were close to the glass. So after analyzing their graphical representation, a possible response might be the singer sings close to the glass, so all the sound intensity hits the glass. I also want to highlight that this activity also demonstrates a convergence with math. And so students engage in science and engineering practice 4, analyzing and interpreting data, and also practice number 5, using mathematical and computational thinking. So again, in this activity, students are going to be thinking about, and you notice with the arrow there, how does this activity help us build a better understanding of what happened with that anchoring phenomena, with that glass breaking and what that singer did. So the unit phenomena tracker is a great classroom tool which clearly defines each learning activity and how it builds towards a better understanding of the phenomenon. So it informs the student about their own learning in a cohesive way as they go through the unit, and they may refer to it at the end of the unit when it's time to write their end of unit gapless explanation. So take a moment and think about what new ideas were introduced in this activity, and how might these ideas support students' changes in thinking about the phenomena. So we'll take a look and see what were some of those ideas that were introduced during this activity by looking at that unit phenomena tracker. If you'd like to type in the chat any of those ideas, or feel free to unmute yourself and share out? Or in other words, what other concepts and ideas did they learn during this investigation? Lilia mentions the glass can be broken with a vibration, so possibly maybe learning about vibration. And it says sound intensity and sound energy are related. They might even start learning what, sound is measured in decibels. What does that mean? What's a decibel? How is sound measured? Okay, I think we'll be ready for our next slide. So after that sense-making activity, students can have an opportunity to revise their initial models, and teachers may differentiate by providing sentence frames and sticky notes of various colors for different purposes. As shown on the screen here, it can be used the green for revisions, orange for adding new ideas, blue for removing or if they will need to find out more, and then the purple for possibly any additional questions they might have around that phenomena or what else they might need to know. So recall also, I want to point out to recall that students should revise their models at least once in the middle of a unit. And the next slide, we'll see that here's a mid-unit revision and what it might look like. And take a moment and think about, what do you notice about Oliver's revised models? So this is his mid-unit revision, and you'll see those sticky notes and sentence frames. Lilia says illustrations were added. Thank you, Lilia. What else do we notice? Does it show that the student has engaged in some more sense making? He added more detailed visuals. Thank you, Sarah. Some of those modeling conventions. Do you notice how he represented sound? Yeah, thank you. Who's that pointing? Oh yeah, it's In Young, right? Thank you, In Young. Those little curved lines to represent sound. So you're able to see, giving that student an opportunity to revise their models. They're addressing their own, possibly their own misconceptions and modifying, changing, and adding on to their thinking, which is again the goal of the goal of the teacher. Next slide. And so here we go back to the NGSS storyline. And again, it shows how each lesson and sense-making activity guides students' learning to answer the anchoring phenomena, and finally getting to that final explanation that includes those science ideas that were introduced throughout each of those lessons. Okay, and then now Craig will be guiding you through our next breakout room activity.
There's a question in the chat about how this
Oh.
might look in kindergarten.
Oh, that's a good question.
Yes, so that is coming up. We're going to get a chance to dive in and look at that. So in the next part here, we're gonna provide you some time to jump in to your curriculum, to your grade level, to the unit that either you're on or you're about to enter, and in your breakout room, working at grade levels, you're going to complete the chart that's coming up on the next slide. You'll be using the participant slide deck. Sorry, In Young, if you can go back one, sorry about that. So on the participant slide deck, have we given that link out already? We have, yes, they've already looked at it. So on the participant slide deck, slides 11 through 13 are going to be for Amplify, and slides 14 through 17 for FOSS. Okay, thank you, Enya. So what you're going to be doing is you're going to be looking at, you're going to be identifying, number one, what is the unit level phenomenon? So put that on top. And then in that first column, what did we do? Okay, what is the sense-making activity? So go through the activities and look for those sense-making activities. And from each sense-making activity, then go to the second column. What did we learn? This through the student lens. What did the students learn? What were the observations or the patterns? And then in the third column, how does that help us explain the phenomenon? What is the connection to the phenomenon? Every lesson should connect to the phenomenon. What is that connection? And then in the last column, any vocabulary words that you might think are key and need to be called out that students will need to learn and know as they go through the unit. They can also use those vocabulary words in their explanations as they're writing their explanations of how things work. Okay, so we're going to send you into breakout rooms. The link is in the deck. You get a forced copy to the participant slide deck. And then you're going to go to the directions on slide 10. And then slides 11 through 13 are how you're going to access the units for Amplify. You'll see on slide 12 there is once again reminding you to look at the unit map and also the coherence flow chart. And then for FOSS, I'll go to the FOSS breakout room and we'll talk, Carla. All right, are we ready? Was there anything else that I'm forgetting? Oh, how much time are we doing this for? I don't remember.
We had
We'll
thought
aim for 10
ideally.
minutes.
Yeah.
That sounds good. All right, so we'll do 10 minutes. We'll give you 10 minutes. You actually have some time to do some good planning here. So 10 minutes and we'll come back in 10 minutes. All right, Lilia, let's see. It's not working for you, the participant slide deck. You're clicking the link there.
If you already opened it previously, it should be, it's going to prompt you to make a new copy, which you don't need to if you already have a copy open.
It's not, when I click it, nothing happens. I haven't opened it. I lost all my information, so I never clicked. Remember, I was driving.
Okay.
So this is the first time that I click it and it didn't let me open it.
Hmm.
But I'll go to the room and see what my peers are doing. Hopefully. Thank you.
Maybe it's behind a window.
I'll look right now. Thank you very much.
Okay.
And I'm gonna join. Thank you.
All right.
Hi, Craig. Can I
Hello.
be assigned? Sorry, my headset fell down. Can I be assigned to third grade? Is that okay? I think I was put in the wrong room.
Oh, yeah.
Thank you.
You're welcome. Let's see. Third grade's going to be in room 4. Thank you. All right, I'm going to go to the FOSS room. Bye.
Can you stop recording before you go, please?
Oh, I can do that. I'll pause it.